Hello, my name is Liam Smith. My group members are Alex Kingsley and Sam Bulio. Our capstone is named UW-Bot. It is a warehouse exploration robot. So we'll run you through a quick agenda. Sam is going to run you through the technical overview. I will then follow up with our technical stewardship focus. Alex will then take us down the road of the value tensions. Finally, we will go through our technical stewardship behaviors and our final reflections.
To give a brief technical summary of our project, there are a number of robots that are currently used commercially, but many of them struggle with positioning in cluttered and dynamic environments. Some robots address this and are used in warehouse environments for moving pallets, shipments, and collecting inventory, but they have a number of drawbacks. Many of these use cameras that can struggle with changes in lighting or require major infrastructural changes for them to be integrated in the workspace. To attempt to solve this problem, our team has tried to use a sensor fusion pairing, including ultra-wideband transceivers and a high-power LiDAR. In theory, the LiDAR would allow us to autonomously navigate, and the ultra-wideband, or UWB, could provide fixed positioning data to adjust for deviations that occur in path planning. In terms of our design, we built a PCB that would integrate with the power supply on the vehicle, and this would collect our fixed positioning data, allowing us to determine the position of the car and whether or not we were in line of sight between the transmitter and the receiver. The parameters associated with our UWB subsystem could then be used in combination with the LiDAR to enhance the quality of autonomous navigation. Although the full integration of the UWB subsystem and LiDAR path planning could not be achieved due to time constraints, the framework we intended to use for the two processes has been finished. Once fully integrated, it is thought that an operator in the real world would be able to click on a location in a map, like shown here in this slide, and the vehicle would begin to autonomously drive to the location while sampling UWB data to correct for misplotted paths or deviations off course. Considering this, the main technical objectives associated with this project included investigating the viability of a specific sensor fusion pairing for autonomous driving in a dynamic warehouse environment. By detecting and mitigating non-line of sight, we would provide our autonomous navigation framework with highly accurate positioning data to ensure it is as accurate as possible. The intended effects of this project is that it would serve as a proof of concept for future research and other sensor fusion iterations to improve upon robotic vehicle technology. We evaluated our design by considering its efficiency, effectiveness, and practicality, and that it might serve as a real alternative to existing solutions.
Tech stewardship in motion. All of the design work we underwent was held to high standards for technical stewardship, ensuring that we adhered to the technical and responsible control of our technical impacts. Our first stretch question is, how are we engaging deep specializations and a wide range of perspectives and expertise? We chose to highlight this question as much of the work we undertook was highly specialized. For this reason, we felt obligated as tech stewards to do our due diligence and verify that the work we're doing is valid and valuable work. Our second stretch question is, how are we utilizing tried and true approaches and exploring new ones? This question pairs perfectly with our project as we set out to discover the viability of a new sensor fusion combo. To make this a successful project, we required to use currently existing tried and true solutions that we then modified to suit our needs and combine them into a totally new sensor fusion pair. The final stretch question is, how are our efforts effectively utilizing our team's resources and helping develop long-term potential? One large resource we have is that we have a cross-discipline team consisting of electrical and computer engineers. This gives us the advantage of allowing the strength of each member to shine while also expanding our horizons to develop on new technology, but our own skills in ways that we facilitate new developments and opportunities in the future.
In our project, we thought extensively about the idea of value tensions, which are important to understanding tech stewardship in our project. These tensions occur when two important values seem to have conflict with each other, but both are needed for a successful design. In traditional engineering, we often think in terms of trade-offs, which we pick one option over another. However, in this case, these are not problems to be solved by choosing a single side. Instead, they are polarities, meaning both sides have value, and both sides can also create problems if taken too far. For example, innovation is critical for improving robotic systems, but too much focus on innovation without stability can lead to unreliable or unsafe designs. Similarly, increasing efficiency through automation benefits organizations but can negatively impact workers and communities if not handled carefully. To better understand and manage these tensions, we use a tool called polarity mapping. This helps us visualize the positive outcomes of each side, as well as the risks that can occur when we focus too much on one side and neglect another. By thinking in terms of balance rather than choice, we can make more responsible decisions. This approach aligns directly with tech stewardship because it forces us to consider not just what we can build, but how other designs affect people, systems, and long-term outcomes. This polarity map focuses on innovation versus stability, which is a key tension in our project. On the innovation side, the benefits are clear. By exploring new sensor fusion techniques and integrating LiDAR with UWB, we can potentially achieve more accurate and adaptive navigation. This allows us to push the boundaries of what current warehouse robots can do and opens the door to future advancements. However, if we lean too far into innovation, we start to see negative consequences. New approaches may not be fully tested, which can introduce bugs, unreliable behavior, or safety risks. In a real-world environment like a warehouse, this could lead to system failures or even accidents. On the other hand, stability emphasizes proven methods and reliability. Using well-established technologies ensures consistent performance, easier implementation, and greater trust in the system. This is especially important for safety-critical environments. But if we focus too heavily on stability, we risk stagnation. The system may become outdated, less competitive, and unable to address known limitations in existing technologies. The key insight here is that both sides are necessary. Innovation drives improvement, while stability ensures reliability. As tech stewards, our responsibility is to balance these forces, introducing new ideas carefully while maintaining a dependable system. Next, we looked at care for organization versus care for community, which is one of the most impactful aspects of our project. From the organizational perspective, automation offers significant benefits. It can increase efficiency, reduce human error, improve safety in hazardous environments, and lower operational costs. For companies, this leads to higher productivity and scalability. However, if we push too far in this direction, the negative consequences become clear. Increased automation can lead to job displacement, reduced opportunities for workers, and potential harm to local communities that rely on these jobs. This can create economical and social challenges that extend beyond the workplace. On the other side, prioritizing care for the community means considering how technologies affect workers and society. This could involve designing systems that support human workers, improve safety, or create new types of jobs rather than eliminating them. But focusing too heavily on this side can limit adaptations of new technologies. Organizations may become less efficient, less competitive, and slower to innovate, which can also have long-term economic consequences. This polarity highlights that responsible engineering is not just about performance, it's about impacts. As tech stewards, we must consider how our design can coexist and support other people, rather than simply replacing them. Finally, we looked at reality versus possibility, which reflects the balance between practical constraints and future potential. On the possibility side, we think about what our system could become. This includes more advanced sensor fusion, improved autonomy, and more real-world applications. This perspective drives creativity and long-term innovation, helping us imagine better solutions. However, if we focus too much on possibility, we risk becoming disconnected from reality. The design may become overly complex, unrealistic to implement, or impossible to complete within our time and resource constraints. This can lead to an incomplete system or ideas that never move beyond the planning stage. On the reality side, we focus on what is achievable right now. This includes working within our budget, timeline, and technical limitations. It ensures that we can deliver a functional and reliable proof of concept. But if we lean too far into reality, we may limit ourselves too much. The project could become overly conservative, missing opportunities for innovation or failing to explore ideas that could lead to meaningful improvements. Balancing these two is essential. Possibility pushes us forward while reality keeps us grounded. As tech stewards, we aim to design solutions that are both novel and achievable, ensuring that our work has both immediate value and future potential.
When have we demonstrated tech stewardship? To start, the design of our PCB was highlighted around future use. We could have created the PCB to suit our needs and our needs only. However, we saw the value in designing it so that future students or capstone groups could use our design work for their project as well. Additionally, we were researching different centrifugation pairings. We left no stone unturned. We didn't want to pick any pair at random. It had to fill a gap. That was where we discovered UWB and LiDAR, a relatively untapped sensor fusion combo with elite potential. Finally, if we had our time back, we would focus on making design more human. That means ensuring that the robot is not a direct replacement for real employees, but a tool that we can utilize to make work safe and efficient. Also putting more focus on the misuse of the project. As we see now, with drones being used in warfare, we fear that the UWB LiDAR combo could also be misused to contribute to achievements in unintended industries. What does it mean to be a tech steward? Being a tech steward in design work requires a deep level of research on both the technical and human level. We are responsible for the things we create. Ensuring that the work we do is done with proper intentions and a certain degree of moral and ethical responsibility is taken to ensure the safe and proper use of our inventions. During this project, we have grown substantially as tech stewards. We realize that every invention, good or bad, can lead to new and further developments. It isn't always possible to know the extent of your design will have on an industry. However, we can control our intentions. Knowing that the misuse and unintended consequences can happen, it is vital to ensure that we reflect on the possible impacts and ensure our work is done correctly and for the right reasons. These are our references. Thank you for listening.